Welcome everyone, I'm Alejandra Gomez, a second-year student of the Paleobiology Master Program at Friedrich Alexander University in Germany. I will be talking about our high-resolution assessment of the Valgu event, conodont diversity and oxygen isotope ratios during the early Telychian in the Baltic Basin. It is important to mention that this project is a collaboration between the Friedrich Alexander University and the Tallinn University of Technology. We as geoscientists tend to be interested in periods of changing patterns, and this study is not the exception. Here, we will be focused on the Silurian on events such as Irviken, Mulde, and Lau, which are characterized by positive carbon isotope excursions and high turnover of graptolite and conodont taxa. In addition to the evidence of the episodes of disturbance in the carbon cycle, abrupt positive changes in oxygen isotopes associated with some of these events are attributed to cooling episodes, sea level fluctuations, and potential glaciations. In this project, we assess the biological and geochemical signal of the Valgu event, a minor bioevent in the early Telychian. We test for a substantial decrease in conodont diversity, a positive carbon isotope excursion, as an evidence of a carbon cycle perturbation, and an abrupt positive change in the oxygen isotopes indicating a rapid cooling episode and potential glaciation. But what do we know about the Valgu event? Well, the Valgu event was defined and identified in other sections in Estonia, Sweden, US, and Canada by a decrease in the number of specimens extracted per kilogram and associated with a positive carbon isotope excursion of around 1.3 per mil. To assess the event in a high resolution, we study a limestone marl alternation core section in Estonia, the Nurme core. And before I was involved in this project, Männik did a tremendous work identifying more than 50,000 conodont elements in samples of our interval of interest. This previous work helped us to locate the event interval based on stratigraphic ranges of the datum taxa. We also run some analysis on paleobiodiversity in advance and set up a plan, which included fieldwork, lab work, and also some coding. For this project, Axel and I traveled to Estonia in April last year. We visited the repository where the core is stored. We went in detail through 33 meters of the section and possible event interval. We took some samples to analyze in detail and prepared thin sections back in Germany. We drilled hundreds of samples for carbon isotope measurements, and we picked up monogeneric conodont samples prepared by Peep to measure oxygen isotope ratios for the same intervals from where we already have the extracted and identified conodont elements. Once the sampling and the preparation and the measurements were done, we had a big detailed picture of the Nurme core and also the Valgu event signal. Starting with the facies analysis, we found that the topmost part of the Nurme core consists of bioturbated marlstone to floatstone and some muddy intervals, but basically the dominant biogenetic components are echinoderm fragments, especially crinoids. We also found some brachiopods, shells, and bryozoans. We identified bentonites, some minor possible gaps in the record, and an evident hard ground at the bottom of our 33 meters. But in general, any facies shift was recognized. Based on the conodont information we had, we determined the interval based on species range, but our main purpose was to use the conodont element counts to analyze paleobiodiversity. However, first we had to correct the effect of uneven sample size by rarefaction, and to do this we use an R package called INEX. The INEX package uses methods of interpolation and extrapolation to estimate diversity indexes, such as species richness, Shannon, or Simpson, based on sample size or coverage base. This means that the diversity is estimated based on a fixed number or a fixed sample size, or based on coverage, which means based on the number of species in each interval. Then we calculated paleobiodiversity for raw data and for rarified samples based on a sample size of 400 conodont elements and coverage based on the species within the sample. The graph shows almost the same trend for the three paleodiversity curves. Still, the species richness calculated based on coverage shows smaller values and smoother changes over time, and during the interval there's no significant drop. The carbon isotope record shows at the bottom and below the hard ground negative carbon isotope values, and limestone and marl values differ, while above the hard ground the limestone and marl values do not differ a lot, and in the record we were able to identify an abrupt increase in the carbon isotopes with a maximum of 2.4 per mil. Then the ratio just falls a bit and follow a constant trend without returning to the negative values. So what we are observing is a positive shift in the carbon isotopes in our section during the Valgu interval. As I mentioned before, we measure oxygen isotope ratios in phosphate for 45 of the same conodont intervals we use for paleobiodiversity analysis. And the isotope ratios were measured at the geocentrum Nurme, and surprisingly, we found that the isotope record was showing us an almost straight line, which suggests no drastic changes in temperature. The changes associated with bentonites, erosive surfaces, and more molly phases also correspond to the maximum and minimum values that appear in the event interval. So to sum up, here is the big picture we got for the Nurme curve. Basically, no significant changes in paleobiodiversity, a positive shift in carbon isotopes, and a straight line in the temperature record. But with this big picture in mind, let's go in detail to the Valgu interval and see what it's showing us. So here it is. Here the paleodiversity analysis doesn't show us a significant change in the trend. Then, contrary to our hypothesis, we didn't find a substantial decrease in the number of species during this interval. The carbon isotopes show us a positive shift and a maximum value within the interval, but this is a positive shift and not an excursion as it is recorded in other sections, such as the Viki core, also in Estonia. Finally, the variation in oxygen isotope ratios, which will translate in changes in temperature, show us both cooling and warming, but those values, the maximum and minimum, correspond to samples collected close to bentonites and possible gaps in the record. In conclusion, here we provide the first high-resolution assessment of the Valgu event by examining a monotonous section. We obtain that the event signal is limited to a positive shift in carbon isotopes. Therefore, here we show that for the Valgu event, phase changes and unconformity bias had strongly influenced the biological and geochemical signals and exaggerate the impact of the event showed in previous studies. This also highlights the differences in the results that we can obtain when we are evaluating signal of any bioevent in a section with and without phase shifts. Thanks so much for your attention, and special thanks to Rina for her hospitality and help during our field trip, to Dani for preparing and letting me get involved in the oxygen isotope sample preparation, and to Birgit for preparing the thin section for us.